So I've been trying for a while now to get my microphone to record well, and naturally, when it finally starts to pick up sounds, it's blown all to hell. I apologize for the sound quality on this one, but it was a good 45 minutes of recording, and I'm not going to redo it. You'll just have to try and put up with it. Bonjour. Bienvenue à la lecture 29. Okay. It's probably not lecture, it's probably conférence or something like that. But this is chapter 7, section 3. We'll be covering Lewis symbols and Lewis structures. These are a way to represent atoms and molecules visually so that you can start to get a handle on them in 3 dimensions and sometimes 2 dimensions so that you can start getting a hold on their structures so that you can better understand the way they interact, the way they behave. So Lewis symbols are for atoms. Lewis structures are for molecules. Okay? Now, you can use Lewis symbols for neutral atoms or for ions, either way. Not usually for transition, well, let's just say, not usually for D or F block, because those have too many electrons, which you'll see in a minute. But yes, for S and P block. Definitely work for S and P block. Okay, so what exactly is a Lewis symbol? Well, it's really simple. You just take the element, you use the symbol from the periodic table, and then you start putting valence electrons around it. So here's sodium, it has a single valence electron. And that's it. Okay, so it's just the elemental symbol and a dot for each valence electron. So calcium has 2, fluorine has 7. Now you'll notice that I'm pairing a lot of these up. That is kind of at your liberty. Okay. For example, calcium has, s electrons, 2 of them. So they're, paired up there in that orbital. So in a way, it's more realistic to show that it is that they're paired on the atom. But you can just as easily draw it as dot separately. The Lewis symbol is more for you to use in helping you to understand bonding and so on. And it doesn't help to be too slavishly bound to the actual orbitals and so on. Okay. But you just put dots around each atom. So here's boron with its 3 valence, or you could draw it like this just as easily. Oxygen has 6 valence electrons, so 1, 2, 3, 4, 5, and 6. Now, for oxygen, you don't necessarily have a whole lot of latitude, just because it has 6 electrons, and only 2 of its valence are going to be, involved in things. Wait a minute. Oh, this over here, this should have been calcium, not carbon. My bad. I forgot the A. All right. It doesn't really matter which side of the symbol the electrons go on. Oxygen can just as easily be represented like this, with the unpaired with the unpaired electrons to the left and to the right. Just one example of how these can help you out. For those of you who have had a little bit of trouble with ionic compounds, getting from the element to the formula for the ionic compound, well, you can use these for that. So here's magnesium, and here's nitrogen. Magnesium has 2 valence electrons. Nitrogen has 5 valence electrons. Now, every element wants to get to the noble octet. They want to look like the next, or the nearest, I should say. They want to look like the nearest noble gas. So what that means is they're going to end up with 8 electrons, okay, looking like, S2P6, okay. So for magnesium nitride, that means that magnesium is going to lose one electron to nitrogen. It's going to lose another electron to nitrogen. Now this magnesium is happy. It doesn't have any more electrons to lose. It looks exactly like the previous noble gas, but you look here, nitrogen is not yet happy. It still has a gap. It only has 7 electrons. So we bring in another magnesium with its 2 valence electrons, and it loses 1. So now nitrogen has 8, and it is happy. But this magnesium over here, it still has an electron, so it's not happy yet. So let's go ahead and bring in another nitrogen, 5 valence electrons. Magnesium can lose its last electron, so now he's happy. But nitrogen, not yet happy, so bring in another magnesium. It loses 2 electrons. Now this nitrogen and this magnesium are both happy. They look like the noble gases. And thus we have 3 of these, 2 of these. The formula is Mg3 and 2. So for those of you who don't like the math, you like pictures a little bit better, this is a perfectly viable way to find the formula for your ionic compounds. Okay. It takes up a little bit of space, but that's okay. And it doesn't have the disadvantage of the, bringing down the charges, because that would tell you calcium 2 oxide 2, which is wrong. Calcium has 2 valence electrons, oxygen has 6, so whoop and whoop. So now they are both happy. It's calcium oxide, a 1-to-1 ratio. So, I mean, it's doable, it gets you a good answer rather quickly, but it takes up a little space. Entirely your call. If you like pictures, if you don't like pictures, as always, find the answer in whatever way works for you. Now let's talk about Lewis structures. A Lewis structure is a way of representing a molecule, and there are some things you need to know. Okay. As with the Lewis symbols, the dots represent electrons. So here we have carbonate, 2-, CO3 2-. The dots represent electrons, so dot equals electron. The lines represent bonds. Okay, so those are where the electrons are shared in between the atoms. So a line is equal to a single bond. A double line is equal to a double bond. And of course a triple line is a triple bond. Okay. Just shows that there are more electrons being shared in between those 2 atoms. So you have a single bond between the 2 oxygens on the bottom, and you have a double bond up here on the top. Okay. A double bond is stronger than a single bond, for example. All right, now for this particular molecule, it has a charge. It's a polyatomic ion. So for ions, we have to put it in brackets and indicate the charge. So because ion. Okay. So indicate the charge by putting it in brackets and actually writing down the charge. So those are the symbols that you'll find on a Lewis structure. Let's talk about some exceptions to the octet rule. Now, most of the elements out there want to have 8 electrons. That is to say, 8 electrons equals 4 bonds. Each bond has 2 electrons each. Okay, so normally that's how your elements get to look like the nearest noble gas when they're making covalent compounds, is by sharing electrons until each one looks around itself and sees 8. But there's some exceptions to that. So first up we have hydrogen. It only needs 2 electrons. The nearest noble gas to hydrogen is helium. It only needs 2 electrons or 1 bond. Okay. In fact, not only does it only need 2, that's all it can have. Okay. It can't have more than 2. All that really has available is that first energy level, the 1s orbital, so only 2 electrons. Next up, we have boron. Boron can stop at 6 electrons. Boron is just kind of weird that way. It's the only one that really does this. It can go to 8, but it can stop at 6. Okay, or 3 bonds. Next up, we have the hypervalent. Oops. The hypervalent elements. This is an N. The hypervalent elements can have more than 8 electrons. Okay, more than 4 bonds. And if you look at the periodic table, the elements that can do this have something in common. They are all from the 3rd row of the periodic table or below. Okay, 3rd row or below. Okay. In the 2nd row, they can't do this. 3rd row or below, they can. The reason for that is because at the 3rd row, you get d orbitals. Okay. 2nd row is just s and p, but 3rd row, they have d orbitals available, and they're empty. 4th row has the 4d orbitals, which are also empty. 5th row, 5d, still empty. So they are available and empty. Because of that, they can form additional bonds if necessary. They're happy to stop with the noble octet, but they don't really have a problem with going further. All right. So that's the exceptions to the octet rule. Okay. Watch out for hydrogen, boron, and anything 3rd row or below. The final exception to the octet rule is the radicals. Radicals, sometimes called free radicals. Okay. A radical is something with an unpaired electron. In molecules, electrons prefer to be paired up. It is very, very rare to have unpaired electrons. Free radicals tend to be highly reactive, so they don't last for long. They'll run around reacting until they run into another radical, and thus electrons get paired up. Okay. So some examples of free radicals are nitric oxide, hydrogen peroxide. Okay. Hydrogen peroxide doesn't start out as a free radical, but it will break up into 2 free radicals with an unpaired electron on the oxygen. That's why hydrogen peroxide is good for, disinfection and cleaning rust off of iron, things like that, because it's got that highly reactive free radical floating around in there. Okay, so free radicals, they exist. They're unhappy. You know you're going to have free radicals when you have an odd number of valence electrons in the molecule. So I'll show you that later on when we're working our way through some examples of Lewis structures. Speaking of Lewis structures, what are the rules for how to draw Lewis structures? First, add up the valence electrons. Okay, so you have a whole bunch of atoms floating around in your molecule. You know, you just add up all the valence electrons each atom brings to the table. Those are the electrons you're going to use to make your bonds and fill out all of your octets. Okay. So for our first example, we're going to do, let's just do carbon dioxide, CO2. So carbon has 4 valence electrons. There are 2 oxygens, each of which brings 6, giving you a total of 16 electrons for this guy. And number 2. You put your central atom in the center and surround it with satellites. All right, so when I say the center, I mean there's one atom that all the other atoms are going to be connected to. At least for these early examples. We're only dealing with with molecules that have a single central atom. Okay, we're not looking at extended geometries, not yet. And satellites are the other atoms bound to that central atom. So for carbon dioxide, carbon is at the middle, and it has oxygens around it. Step 3, draw one bond to each satellite. Okay. And you subtract 2 electrons per bond. Okay. Each bond contains 2 electrons, so you got to remove those. So there's one bond going from carbon to oxygen on the left, another bond going from carbon to oxygen on the right. 2 bonds means you lose 4 electrons. So we have 12 electrons left over. Fill out the octet on each satellite by adding non-bonding pairs, NBP. Okay. A non-bonding pair is a pair of electrons that are sitting on an atom that are not participating in a bond. Okay. So they're paired up, they're happy, but they're not part of a bond. So we fill out the octets on our satellites. That means oxygens in this case. So 1, 2, 3, 4, 5, 6. So now oxygen, the one on the left, looks around itself and sees 2, 4, 6, 8 electrons. It looks at the bond, and even though those 2 electrons are shared with carbon, it still counts both of them toward oxygen. Okay, we can do the same thing with the oxygen on the right. 4, 6. And that oxygen will also look around itself and see 8 electrons. Again, the two electrons within the bond that it has to carbon both count toward oxygen. They'll also count toward carbon. That's the great thing about bonds. Because they're shared, each atom gets to claim those electrons for its own octet. So we've used up 2, 4, 6, that's a 4, 8, 10, 12 electrons, making these non-bonding pairs. Okay? So we use up 12 electrons. We're left with 0 electrons. Now, step 5 is any remaining electrons go on center atom as non-bonding pairs. Now, in this case, we don't have any atoms left over. We don't have any electrons left over, so none will be going on carbon as non-bonding pairs. Carbon's lost. There will be other examples of that later. Plenty of molecules like that. Okay, and 6, if needed, fill out central atoms octet by changing satellite non-bonding pairs into double or triple bonds. Okay. So carbon only sees 4 electrons. Okay. 2 on the left, 2 on the right. Okay. It needs 8 to be happy. We don't have any more electrons to give it. So instead, we're going to be transforming non-bonding pairs into multiple bonds. So I recommend when you start making Lewis structures, either write in pencil or leave plenty of room, because what you'll need to do is cross out a non-bonding pair, turn it into a double bond. Now, this oxygen on the left still sees 8 electrons. 2 from that non-bonding pair, 4 from that non-bonding pair, 6, and 8. So that oxygen is still happy, and now carbon sees 6 electrons. 2, 4, 6. Still not happy for that carbon. So what we can do is we can come over here to the other oxygen, cross out another non-bonding pair, and turn it into a double bond. Now carbon has 8 electrons, and each oxygen has 2, 4, 6, 8 electrons. So now all 3 atoms are happy. I could just as easily have turned another non-bonding pair from the left into a bond, making it a triple bond and a single bond, but these 2 oxygens are perfectly identical. There's no reason for one oxygen to have a triple bond, the other oxygen to have a single bond. Might as well both be double bonds. Okay? Nature likes symmetry like that. So yes, this looks kind of messy right now, which is why go ahead, redraw it, and there we have the Lewis structure for carbon dioxide. Let's go ahead and do some more examples. How about that? Here's something that might sound a little familiar. Sulfur trioxide. Something that could have been produced in the last lab you did. Okay, so sulfur brings 6 electrons to the table. Oxygen brings 6, and there are 3 oxygens, giving us a total of 24 electrons. So sulfur goes in the middle. We surround it with oxygens. Now we draw a single bond to each of those oxygens. 2, 4, 6. 3 bonds uses up 6 electrons. So we have 18 electrons left. So 2, 4, 6 on the first oxygen. 8, 10, 12, 14, 16, 18. And so we've used up the last of our electrons, filling in non-bonding pairs on our oxygens. So we might as well, we have to go ahead and turn a non-bonding pair into a double bond. You can choose any of the 3 oxygens, and there you go. That is the structure for sulfur trioxide. The actual structure is slightly different, but not really. We'll be getting into that in the next section. Don't worry. There's always ways to make it more complicated. First, let's go ahead and just keep on looking at examples. Keep on churning through them. Next up, let's do methane. Methane, or the gas coming from cow burps that's contributing to global warming, is CH4. Okay. Carbon contributes 4 valence electrons. There are 4 hydrogens, each contributing 1, for a total of 8 electrons. So we put carbon in the middle, surround it with hydrogen atoms, and we make a single bond to each hydrogen atom. And that uses up 8 electrons. We're left with 0, and we're done. Remember, each hydrogen only needs 2. Any more than that, and you'd be going into the next energy level. Hydrogen would be really unhappy. And carbon looks around itself, sees 4 bonds. That's 2, 4, 6, 8. Carbon is nice and happy. So this is the Lewis structure for methane. Now let's go ahead and do ammonia. And while we're at it, ammonium. So ammonia is NH3. Ammonium is NH4+. So ammonia, we have nitrogen with 5, and then we have 3 hydrogens, each giving us 1 for a total of 8 electrons. Now, over here on the right, ammonium, we have 5 electrons from nitrogen. We have 4 hydrogens, each one giving us 1. Now, here's the thing. We have this charge. A charged species will have a slightly different number of electrons. You always subtract the charge. Okay? So because it has a positive charge, that means it's lost 1 electron. A negative charge would mean it's gained an electron. So you add up all the valence electrons, you subtract the charge on your compound. So 5 plus 4 minus 1 is 8 electrons. So ammonia, we have N, H, H, H. Ammonium is N, H, 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 H. Now you go ahead and you draw a bond from each hydrogen to nitrogen. For ammonia, those 3 bonds use up 6 electrons. We have 2 left over. For ammonium, 4 hydrogens, 4 bonds, uses up all 8 electrons. Now, neither of these molecules is done. Okay. Ordinarily, if you have electrons left over after you've drawn in your bonds, you would put them on the satellite atoms to fill out the octet. But remember, hydrogen's an exception. It doesn't take more than 2. So instead, we go to the next rule, and those 2 will go on nitrogen as a non-bonding pair. So now nitrogen looks around and sees 2, 4, 6, 8. So nitrogen is happy. Each of the hydrogens is happy. That's ammonia. And for ammonium, nitrogen sees 2, 4, 6, 8, those 4 bonds. Each hydrogen sees 2, so all 4 of them are happy. But we're not done with this Lewis structure because it's an ion. We need to indicate the charge on the structure. So we put square brackets around it, and we put the charge on it. Don't forget the charge. You always have to indicate the charge. Let's do some more sulfur compounds. How about sulfur hexafluoride, SF6? Sulfur gives us 6 electrons. There are 6 fluorines, each of which gives us 7. So let's make that clear. 6 electrons, and then 6 times 7 electrons gives us 48 electrons. So, sulfur, fluorine, 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 fluorine. Let's go ahead and draw a bond from sulfur to each of our fluorines. 2, 3, 4, 5, 6. 6 bonds means 12 electrons gone. We're left with 36. Now we start filling in the non-bonding pairs on fluorine. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. That uses up all of our electrons. And fluorine, each one of these fluorines looks around itself and sees 2, 4, 6, 8 electrons. So they're all happy. What about sulfur? Sulfur looks around itself and sees 2, 4, 6, 8, 10, 12 electrons. Sulfur is in the third row. It has empty 3d orbitals available. It can have an expanded octet. So everyone here is happy. This is the Lewis structure for sulfur hexafluoride. Let's go ahead and do carbonate. It's one I showed you earlier. CO3 2-. So carbon gives us 4 electrons. There are 3 oxygens, giving us 6 electrons each. We subtract the charge, -2. 4 plus 18 minus -2, that means +2. So that gives us a total of 24 electrons. So carbon, oxygen, 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 bond, 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 James Bond. So that uses up 6 of our 24 electrons, leaving us with 18. Let's go ahead and fill in the octets around oxygen. And that is 18 electrons. We have 0 electrons left. Carbon is not yet happy. It has 2, 4, 6. It needs more electrons. Let's go ahead and steal the non-bonding pair from the oxygen up top. Now, all 4 atoms are happy. Still not quite yet done because negative charge, square brackets, 2-. Now we're done. That is the Lewis structure for carbonate. Now we can keep on going. Let's look at boron trifluoride, BF3. Well, boron gives us 3 electrons. Fluorine is 3, 7 electrons, giving us a total of 24 electrons. Yes, that happens a lot. All right, so boron in the middle, fluorine, fluorine, fluorine. 1, 2, 3 bonds gives us 6 electrons. That's 18 electrons left. Now 2, 4, 6, 8, 10, 12, 14, 16, 18. That uses up our 18 electrons, and we have 0 electrons left. And now we're done. We don't need to form any double bonds. Boron can stop at 6. Remember, it is one of the exceptions to the octet rule. Boron is okay, just having 3. And now we're done. Now how about phosphorus let's mix it up a little bit. Let's make it pentachloride. So, there's 5 electrons from phosphorus, 5 chlorines with 7 electrons each, gives us a total of 40 electrons. So phosphorus, chlorine, 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 chlorine. 1, 2, 3, 4, 5 bonds use up 10 electrons, and we have 30 left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. And that uses up all 30 electrons, and we have 0 electrons left over. Phosphorus, like sulfur, is in the third row, so it has 3d orbitals. It can have an expanded octet of 10 electrons. So this is the structure for phosphorus pentachloride. Obviously, I would be seriously remiss if I didn't show you, something like ozone. Ozone is 3 oxygen atoms bound together. So, Oxygen, there are 3 of them, giving us 6 electrons each for a total of 18 electrons. And the way this works is it's just oxygen, oxygen, oxygen. It's an alien. All right, okay. So, bond, bond. So that uses up 4. We have 14 electrons left over. So 2, 4, 6, 8, 10, 12. We filled in our satellites using up 12 electrons. We have 2 left. Those go on the central oxygen. And we're all out of electrons. Now each of our satellites is happy. 2, 4, 6, 8. 2, 4, 6, 8. But our central oxygen is unhappy. 2, 4, 6. Unhappy. Sad little oxygen. So the way we make it happy is by taking a non-bonding pair off of one of the satellites, turning it into a double bond. And now it has 8. And now the central oxygen is happy. And this is the structure of ozone. Let's make it a little bit clearer. O, 2, 1, and 3 non-bonding pairs. And I promised I'd show you nitric oxide. Nitric oxide is a free radical. It has 5 electrons from nitrogen plus 6 from oxygen for a total of 11. So nitrogen, oxygen, we make a bond, and that uses up 2. We have 9 electrons left over. 2, 4, 6, 8, 9. We're all out of electrons. Oxygen has 8. Nitrogen has 1, 2, 3, 4, 5. So let's go ahead and get nitrogen as close as we can to the noble octet by transforming a non-bonding pair of oxygen into a double bond. Now nitrogen has 7, oxygen still has 8. That's the closest you can get to the noble octet. Nitrogen is only in the second row. It doesn't have any d orbitals available, so it can't go more than 8. So only a double bond. And this is the structure for nitric oxide. Now, I really strongly recommend you get plenty of practice. Practice is a good way to get somewhat good at drawing Lewis structures. And I will see you in the next lecture for section 4 of chapter 7.